Today we'll briefly review the previous course about the controllability for nonlinear systems. I will give you a quick comparison with controllability of linear systems. So we mentioned that for the nonlinear system to be controllable, you need to evaluate these conditions. Remember that for linear system, we evaluate a C matrix. In a C matrix, we evaluate a B column vector, AB, A squared B, and etc. And we say if C is a full-rank matrix, it's controllable for linear system. And in the nonlinear systems, the matrix to be evaluated will be this, right? So now we do a column-wise comparison. So compared to B here, we put F G D squared, lib bracket FG, right? The lib bracket of F and G means the derivative of y along the flow generated by x. That means that given the change of x, what will be the change of y? Because x, y are component together. You can consider this as a capital X, capital Y. These two are component together because the control input can change the x, and x appears in both in here and here. So both two are component together. So using the combination of f, y, because they are coupled together, we want to see how they were so if B is 0, 0, 1 and next time is 0, 1, 0, that means that B is the coefficient of control input. And control input coming to a system to affect the third element, right? Because it's non-zero. But at the next time step, I evaluate A times B because the change of the third element can affect another elements 1 or 2, depend on what A is. So it's kind of propagate in time that how this control input can affect another element. If it's 0, 1, 0, that means this A, the contribution of A in this product is that element can change the second element based on the natural dynamics of A. And for the nonlinear case, it's similar, right? We want to see if at the first time we use this, and the next time we want to evaluate how does different combination of your control input. Now we add one more F, right? So it's one more control input. So we want to see how this combination of control input can change your column vectors, evaluate if it's full-rank. This is a necessary condition for controllability of nonlinear systems. If this doesn't hold, the nonlinear system will not be controllable. Necessary condition, okay? You can consider span as a linear combination. Let's start from a simpler case, 2 by 1. So in a 2D plane, say x1 is 1, 0. So x1 is 1, 0. 1, 0. x2 is 1, 1. Right? Okay. What is span of x1 and x2? It's a linear combination of these two. Okay, otherwise it's equal to alpha times x1 plus beta times x2 for any alpha, beta belong to a real number. Okay, linear combinations. For example, x3 is 2x1 plus 3x2. Okay, alpha is 2, beta is 3. That will be this 2 times x1, 3 times x3, right? So this is x3. Okay, linear combination. Span is a space, so x3 is belong to this space. Why is a space? Because it's a combination of these two vectors. Combination. So combination is anywhere in this 2D plane will be the span of these two, right? Because this space, this combination of these two can cover the whole space in this 2D plane, right? So now let's go to a 3D case. Okay, let's say maybe FG. F is here. What is G? Here, right? What's the span of FG? 2D plane, right? Span of FG will be the XY plane. It's anywhere in this plane. Okay, and if I say FGH, if I say H is 0, 0, 1, the question is H belong to the span of FG? The necessary condition for controllability is the bracket of F and G, which is also some three-dimensional, some dimension equal to this, is a column vector, right? This column vector can be belong to the space of F, the combination of M and G, okay? Because if the F is here, G is here, and the D bracket is still in here, is still in this 2D plane, then any state in this with Z components is not controllable, right? So if your Z bracket is in the span of this, otherwise, if your Z bracket is still in this XYZ plane, then it's possible that no matter how many combinations of your control input, that will still in this 2D plane, right? And if your state that you want to control is in the Z plane, you will never be able to control. So it's a necessary condition. So all these have been recorded, so we can go back to review several times. Okay. And next topic, which is also very important, especially functions. So the first topic is limit cycles. That should be easy. Next is functions. Okay. The reason we talk about functions is ODE is kind of functions. There are many properties to be discussed. And next will be existence and uniqueness of solutions. And remember, as I say in the first class, that for nonlinear differential equations, usually the solution is hard to be solved. But since it's hard to be solved, we assume that it cannot be solved. So because it cannot solve, how you evaluate that the solution exists? Or if it exists, is it unique? Okay, that's two different questions. Exist could be one solution, two solutions, many solutions. But is the solution unique? Means it's only one solution or not? If a system has multiple solutions, you could be in trouble, because how you know, given a control, your car or your robot will go, it's hard to determine, right? So it's better to have a unique solution. It's better to prove the stability. Then will be a stability and stable, unstable, and those stabilities. So for limit cycle, I believe you have seen this kind of system before. So the definition for a limit cycle is xt plus capital T will equal to xt. This t is a positive constant. It's a time which is positive, and for some capital T. Okay. So this t, capital T, you can consider as a period, 周期. Okay. So after a period capital T, the state will repeat. After, imagine that this is a phase portrait. The x-axis is velocity, y-axis is the position. So it's a phase portrait. So after some capital T periods, it will come back again and forever, right? Repeat. So it's a limit cycle. We know it's, for this case, dynamics is this, and the period is this. We want to see if how you define this, it is stable or not. And usually, the amplitude of this oscillation is independent of initial conditions. For example, no matter where you release, if you release from here, eventually you will oscillate with this amplitude, right? It's independent of your initial condition. Usually it's stable, because it doesn't diverge. It just stay in some orbit. Okay, so we call it stable, but it's not asymptotically stable. So in this case, no matter where you release, if you start from here, or here, eventually it will never leave this. Eventually, the solution, the limit cycle will be this. So if you move from outside of this orbit, you will converge to this orbit. If your initial condition is from here, it will go outwards until it reaches this orbit. So this is the case with epsilon 0.2. For epsilon 0.1, you will obtain a little bit different phase portrait, but it's still stable. If you come from outside, eventually you will reach to this orbit and stay on this orbit. If you come, the initial condition is from inside, you will go outward until it reaches to this orbit. So the previous case is stable, right? Now, what is unstable? This is unstable on the right-hand side. So, for example, if you put from here, your initial condition is here, it can go outwards and diverge, right? So it's unstable. Even though that if you start from inside, it might converge to the origin. Some other location, it can go unstable. So you cannot say it's stable. You can only conclude it's unstable. Stable means usually in general, okay? No matter where you are, you should guarantee that it will be stable. So next, so functions. Function is more important. So why do we talk about functions? Imagine that nonlinear, we mentioned for a nonlinear system like this. We can solve for the solution, right? C depends on the initial condition. But for nonlinear systems, maybe it's solvable, maybe no one knows. So assume the worst case that we don't know the solution. Okay, we don't know the solution. Then if the solution maybe doesn't exist, or it has multiple solutions. Okay, so the reason we talk about function is, given this kind of dynamics, you want to evaluate the existence of solutions, uniqueness of solutions. Okay. Function is continuous if, say, any x1, x2, they are very close. They are in a range of delta. They are very close. And the function of x1 and x2, the difference will be also smaller than epsilon. Okay, delta and epsilon are any positive numbers. And if it satisfies this condition, we say the function is continuous. For this example, is it continuous? So obviously it's not continuous around 0, right? Because on the left-hand side of x equal to 0, it's 0. On the left-hand side of 0, which denotes as 0 minus, it's 0 minus means on the left, a little bit left-hand side of 0 plus means the right-hand side of 0 is 1. In other words, it cannot jump. How about the next example? Is it continuous? How about next? What is a differentiable functions? It's defined as a function is differentiable if the derivative of f, which is defined as f of x plus h minus f of x divided by h. H is a small positive number, okay? And h approach to 0 had to be exist. So in this case, you need to evaluate both from the left and the right-hand side around x. Okay. These two have to be equal. Then you can say it's differentiable. Okay. This implies this, and vice versa. Okay. In other words, in this example, what does this part mean? It means we evaluate as h approach to the right-hand side of 0. What is the right-hand side of 0? Right-hand side of 0. So h is right-hand side of 0. Okay. Assume that we use x equal to 0, h is 0. Okay, h is 0, x is 0, x is 0, h is 0. Okay, we evaluate. So here it means we want to evaluate the derivative at x equal to 0, right? Which is here. We want to evaluate if the function at here is differentiable or not, right? So x is 0, h is 0. So at x is 0, and h is on the right-hand side of 0. Okay, means it's a little bit greater than 0, which is here. Right? 0 is here. Here is 0 plus. Okay, and what is this? So at f 0 plus 0 plus minus fx, which is 0, divided by 0 plus. Okay. 那也就是 which means is the slope of this, right? And what's the slope? if it's a straight line and it's 1, 1, then the slope will be 1, 对不对? And how about this part? Again, x is 0. Here is 0 minus 0, 0 minus. Which means we evaluate, here is 0 and 0 minus. So it's on the left-hand side, right? And here is 0. So we want to see the slope of this, which is 0, right? And this is 1. So are they equal? They are not equal. So it's not differentiable. Is this function differentiable or not? Yeah, right. So this is an exponential function. So it's differentiable everywhere. And in this function, it's differentiable everywhere except at 0. And is it continuous? Is this function continuous? It's continuous. Continuous doesn't mean it's differentiable, right? But differentiable means it's continuous. Okay? A function is differentiable, then it had to be continuous, but not vice versa. Then one more step forward, continually differentiable. What is continually differentiable? You know continuous, you know differentiable. Then continually differentiable means you differentiate the function and check if f prime is continuous everywhere. Let's step back for differentiable. What does this say? It says exist, right? What is continually differentiable? What's the difference? Again, it had to be exist. Any others? Continuous. Right? So back to this example. It's not differentiable, right? Because if I say from here to here, it's differentiable in this region. Yes, right? But it's not differentiable in this region because of it here. And the second example had to be given this f, then can take the time derivative of this f and plot out the function, evaluate if it's continuous. Okay. If that happens, it's continually differentiable. So in this case, it's continually differentiable. Continually differentiable. We call C1. Continuous, and it's first order differentiable. Continually differentiable. But what if only, so what is a differentiable function looks like in here? It might be this and this. Some function with derivative of this is only differentiable. It is a continually differentiable. It's a C1 function. Okay, continuous. First derivative is continuous because C1. If the second derivative is continuous, we call it C2. What is C0? Continuous, but not differentiable. You can imagine this power here is the how many times of differentiation, and C means it's continuous. So it's not differentiable, but it's continuous. C1 means derivative is continuous. Yeah, and sine function is also C1, continually differentiable. Is there any function that is differentiable but is not C1? Means it's differentiable, but the derivative is not continuous. Yes, this function. Why? The derivative of this function is not continuous at 0. When x is 0, it's 0, right? At the origin, right? But when it's not 0, it's very close to 0, right? If you for 0 plus, it's very close to 0. So it's continuous. But when you take the time derivative, if you substitute 0 to here, what will you get? For C1, this function had to be fx. For continually differentiable, the derivative of this function had to be continuous. That means it's 0 at 0, but when it's not 0 at 0, there should be no jump for the f prime, right? F prime cannot jump. So if you substitute 0 to here, you should get 0. But when you substitute 0 to there, it's not 0. Why? When you substitute 0 to here, 2x is 0, okay? And the upper bound of this sine function is 1. Okay, so the second term will be 0. But how about this one? When x is very close to 0, but not 0, very close to 0, what's this value? It's between -1 and 1. But you never know where it is, right? So it's not 0 at 0. C1 嘛 ，OK， derivative 必须连续嘛，所以在0的时候它是0，那在接近于0的时候它应该也是0，所以你带0进去它应该也会是0，但是你带0进去它不会是0，你甚至不知道它多少，对不对 ？Let's focus on this. X equal to 0. What's the value of this? Right? Could be -1, could be 1, around 0. Even for a very small 0. So as long as x changes, this 1 changes around -1 and 1. So it will never be 0. Okay? So this function is differentiable, but not continually differentiable. Okay? So next is Diffuse condition. So basically, it's not very hard to understand. A function of f which is mapping from x to y is called diffuse continuous. If there exists a real number L for some x1, x2 belong to x. So L basically, the physical meaning is the slope upper bound. Here's slope given any x1, x2. The absolute value of slope cannot be greater than some positive constant. So it's the upper bound of the slope. So if this condition is satisfied, we say this diffuse condition. So basically, this implies the function has a bounded variation. So let's check out this. So you will agree that this function is differentiable everywhere, but not at 0, right? So it's differentiable everywhere, but not at 0. Right. And its derivative is what? Here is -1. Here is 1. Okay, so it's not continually differentiable. And it's differentiable everywhere, but not at 0. Okay, so is it diffuse? Yes, it's diffuse. Why? In here, the slope are bounded, right? How about in here? If you evaluate this condition, okay, given any x, any x1, x2, this will be bounded on this function. Even though the derivative is not continuous, but that condition will be bounded. As long as the slope doesn't go to infinity, the condition will hold. What will I conclude for the example 1 is diffuse. A function who is diffuse doesn't imply it's differentiable. What's the problem with the second example? Its derivative with respect to x is this. And what's the problem? So remember that we say diffuse continuous condition means that the slope had to be bounded. But as you take the partial of f, when x approaching 0, this value will go to infinity, right? Which implies the slope is not bounded. So it's not diffuse continuous. So continuous functions are not globally diffuse. Globally means everywhere. Everywhere means for any x. Okay, so the first example here is not global because here, if only one point is not differentiable, then it's not globally differentiable or continually differentiable. Okay, it's everywhere, but not here. Same as second example. So in the second example, for this function, it looks like the configuration is like this. Yeah. So the slope around 0 is very large. So all these examples are very spatial. I give you all these examples to facilitate your study. But usually for general mechanical system, the dynamics won't be looking like this. So if you zoom in here, it's like this. Online. So I'll give you some examples. Sine of 1 over x. So you can see that as x go to 0, it oscillates around -1 and 1. Okay, the frequency becomes higher and higher. So it's not sure that what's the value of sine 1 over x at 0. Okay. As x go to 0, the frequency will change very, very rapidly, but the value is bounded by -1 and 1. Okay, so you never know what's the value at x equal to 0. So you can, after you go home, you can check this website for some special case. Okay, this is the example we just discussed. So there are some other examples you can check out. So what's the problem with this one? So similarly, it's not differentiable at x equal to 0 because it's even not defined, right? For 1 over 0, it's not even defined. Okay, so of course that implies it's not differentiable, and the slope will be very high as you substitute x equal to 0. This goes to infinity, so it's not Lipschitz continuous. So the conclusion for these three examples is we know Lipschitz doesn't imply differentiable. How about the reverse? How about differentiable function? Does it imply Lipschitz? Not really. But what is true is for continuously differentiable C1 function, it has to be Lipschitz continuous. Next, this part is more important than previous part because previous part is the tools that will be used in this section. So why we care about existence and uniqueness? So go back to the ODE, mechanical system or any dynamics systems described by ODE. So here you can see here f is a function. Could be linear function, nonlinear functions. If it's a linear function and given an initial condition, I can solve for x. If you are not lucky, this is nonlinear functions. There is no way you can solve for the solution given these initial conditions. What you can do is you still can design a controller to evaluate the stability of this system. Stability means your objective is design a controller. And in other words, given any initial conditions, no matter where in the phase portrait, okay, given any initial conditions, now it's x1, x2, phase portrait, okay, given any initial conditions, here. We want to see if you can go to the equilibrium point and conclude that it's asymptotically stable or it's stable, right? So we want to evaluate given any initial conditions. even though we don't know how it will behave because we don't know the solution, right? We still can do that, but we don't know what happened in between. We know it starts from anywhere, it will convert to here. That's what the controller is being designed, okay? We don't know what happened because there's no solution, okay? But now here is, we want to see, given this f function, we want to see that if given these initial conditions, if this path is unique, or if the solution exists. Okay, we don't know the solution, but we want to tell if the solution exists. If it exists, is it unique? So that can be told based on this f. So given this f, if f is a continuous function, continuous, defined in some region, containing some point x0, then there will exist a solution. Okay. So given this, we should be able to have a fast portrait, right? And next, we check if this function is continuous. Defined in some region around x0, right? In other words, here is x0 minus delta. So R is in this region, right? So if this function is continuous in R, okay, everywhere here is continuous, no jump, then there exists a solution defined in this region. If your f satisfies this, which is continuous in this region, okay, then solution exists. Maybe we don't know the solution because it's nonlinear ODE, but we know solution exists only in this region because it's only continuous in this region. This is capital Fx, and so capital Fx is okay. In other words, given this function, when x is on the left hand side is -1, right hand side is 1 for sine function. Okay. If your dynamics is this, okay, and according to that, it says f had to be continuous in some region. Maybe say this is R region, because it's not continuous at 0. So this one might not exist. Okay, it's even hard to solve this one. 有人办法解出这个 solution 是什么？它实际上它是不存在的。If your initial condition is 0, initial condition is 0, there's no solution. Okay, because at 0, this function is not continuous. And back to here, if it's not continuous at x is 0, right? 0 here is not continuous. But if your region, if you change your region R to here, move to the right, we only care about this, okay, this part. So I say the initial condition is 1, okay. Initially is from 1 here. I start from here. Well, you are lucky it has a solution because it's continuous. F is continuous, right? Sometimes it could be one solution, could be two solutions. For example, in this one, okay, the derivative, this square root of x is not continuous or not defined as 0, which implies fx initial condition is at 0. Right? This is not defined. Right? 也就是说 square root of 0 is not defined. 对不对？零可以开根号吗？不行嘛。If your initial condition is from 0, and this is your dynamics, there's no solution. Okay. But if your initial condition is maybe 1, not at 0, okay, not at 0, maybe you got a solution because it's continuous. It's not continuous only at 0, and continuous other way. Okay. So this is for existence. Next, uniqueness. We want to see if the solution is unique. Unique means only one solution. So the previous slides tell you solution exists, but it could be one solution, two solutions. So let me give you an example first. Do you know what's the solution of this, given these initial conditions? In this PDF, I only have this dynamic. When x similarly at 0, the partial of y doesn't exist. Similar to this case, given this dynamics, which is this. If you put 0 at 0, initial condition is 0, you will have two solutions. One is 0. It always at 0. It always stays at 0. Another solution is x equal to t squared divided by 4. If x is t squared divided by 4, what is x dot? What is x dot? Will be 2t4, right? Okay. 4. And what's the dynamics? Sorry, because x is a function of time, so its time derivative and partial derivative are the same. Okay, so these two are the same. Okay, agree? Okay, so this is according to that given this solution, right? Have the time derivative on this one, we obtain this, and this is from the dynamics. The dynamic is x prime equal to square root of x, and given the solution of this is this, so these two are equal. So solution 1 is true. Okay, so it have one solution, two solutions. If it's 0, stay at 0, right? What's the time derivative of 0? 0. It's always 0, so its time derivative is 0. According to the dynamics, the dynamics of x is equal to square root of x. And if x is always 0, the dynamics will also be 0. So these dynamics have multiple solutions. Those solutions exist, but it's not unique. So let's go back to uniqueness. So here, exists as long as it's continuous. But what's the requirement for uniqueness? The requirement is not only f had to be continuous in the domain of R, the derivative have also be continuous. So in other words, C1 f have to be C1 function. This solution will be unique. Okay. I believe everyone here are from with engineering background, right? Here is no pictures, only equations, so it's from mathematics perspective. And if you want to do some control research, it's necessary to get through this, suffer through this process. Okay. And it's very important here because when you submit paper to a very great or very famous journals, they will challenge this. Because you can design controller, right? Controller change this F. Given the dynamics, given the differential, remember in the first day of the class, I say minus plus phi, right? And u equal to minus x minus phi, which give you, so this one is open loop, no control. Open loop substance. This guy is closed loop systems. Given a system, okay, no control, here's your fx, right? After you apply your control here, this is your fx. It has a control component there. In other words, your control can change this capital X, 对吧? And if after the f being changed, you need to, maybe sometimes you need to say the solution exists or the solution is unique. If the solution is not unique, you have to prove every solution that is stable. Okay, that's very tricky. So it's better to design an F that have only unique solution. Sometimes it's hard to do so, but in which case usually it's easy to prove that every solution is stable. So today we talk about functions. Then we talk about existence, uniqueness. All that are very strongly correlated. I guess you have a little bit, you suffer a little bit from this, but that's very important. Okay, these dynamics have multiple solutions here. One red line represents one potential solutions, and it has many solutions. So the solution exists but not unique. So why? Let's evaluate. Let's look at these dynamics. So of course, the capital X. Based on this, this is capital Fx, right? So now let's evaluate Fx existence. What does existence say? If f is continuous, in R in some region, okay, then solution exists. If your initial condition is belong to R, okay, your initial condition start from the region that is where fx is continuous, then there exists a solution. So both of these functions, so f is this, the partial of f is this, okay, and it says both functions are defined for everywhere other than x equal to 0. For each x not equal to 0, there is this unique solution, different open area. This function is defined everywhere, but not at 0. Because at 0, this one goes to infinity. It's not defined. So it's defined for any x not equal to 0, right? Because this is guaranteed for existence, uniqueness, right? Suppose satisfy for x not equal to 0. So unique, the solution will be unique in the open area around x0. So this conclusion is, as long as your initial condition is not 0, it guarantees you will obtain unique solution. What happens if you start from 0? If you start from 0, you will have multiple solutions that are not unique, but it exists. Okay, in this solution in the open area around 0, for initial condition not equal to 0. But if had to be at 0, initial condition had to be 0. If you start at 0, you will have obtained many solutions. So the suffering part have been passed. Now it's easier. Class CK function. C means continuous, K's order of derivative. Okay, CK function means that it's differentiable. A function f is CK if it's the derivatives f prime s double prime TL to fk prime, k's derivative exists. Then we can say f is CK function. So for C0 function is 0 order continuous, so it's just a continuous function. For C1 is first derivative is continuous. So for C infinities, we call it smooth function because it have derivative of all orders. For example, exponential function, sine function, cosine function. Neighborhood. A neighborhood means a neighbor of a point P in a set of capital X. Then we say is a neighborhood of P. It's hard to understand. Maybe I'm fine, but maybe it's for junior graduate student, it's hard to understand. So given a point P, okay, P, let's say P here. P belong to a set X. In this area, we say it's capital X, okay? P is in this set. A neighborhood of a point P is a set of points around P, okay? It's a set of points around P. We call it neighborhood. Every point, we call this is N neighborhood of P and RP. Okay, here. Okay, this is set. So this is a neighborhood set of P. Okay, and this neighborhood set of P is still in capital X, right? In this rectangle. This neighborhood set of points consists of every point Q that satisfies the distance between P and Q is smaller than R. That means any Q point here, the distance is smaller than R, will be in the neighborhood set. And we say if the distance is R, then this every point in this disk is a neighbor of P. Okay. You can consider neighborhood as a set of points around some P. Then that's our neighborhood set. Okay, close to some point. Okay, and here close means within the distance of R. Within the distance of R, all point the K in this disk center at P will be a neighbor of P. To define what is stable, unstable, and asymptotically stable. Stable means that if there exists a delta greater than 0, be any positive value, okay, could be as small as possible. F is a function which is locally diffuse. Locally means not globally. Then an equilibrium point which is at 0 is an equilibrium point if that some initial condition, if you initial condition is star in around this equilibrium point as close as possible, okay, for any time t here. Here's initial condition, okay. If you start around the equilibrium point, it will stay around the equilibrium point forever. Say equilibrium point is here, xe equilibrium point, okay. Equilibrium point, remember for equilibrium point, you substitute equilibrium point into this f. There will be 0. That means the time derivative will be 0 because it's stationary, right? Equilibrium point. So given the equilibrium point, say here, and you have some initial condition x0. Then after maybe the trajectory is his, but after some time t, you will be close. X0 is here. Here's xt. After some time t, this distance is still bounded, smaller than epsilon. Then we call it stable. That means it cannot go to infinity. So for limit cycle oscillation, it's always in this circle, right? No matter where you start from here, you will converge to this cycle. You start from inside, it goes to this orbit. So no matter where you are around the equilibrium point means everywhere on this orbit, you will stay on the orbit. So this is one example of stable. And unstable means it's not stable. In other words, greater than epsilon. Okay, which means it diverges. So equilibrium point is here. Initial condition is here. If you move anywhere in here, okay, which means for this distance is delta. The distance between your equilibrium point and your initial condition is within some constant delta. Then for any time t, be t here, x t equal to 1, x t equal to 2, and x equal to xt, okay? It always remain in the distance of epsilon, which is greater than 0, okay? This distance is smaller than epsilon, then it's stable. So one of the example is limit cycle oscillation, right? In the first slides, it's stable because it always stay here. The radius to the equilibrium point, well, there's no equilibrium point. Anyway, it stay here, okay? It stay here. It doesn't go anywhere. It's stable. Asymptotically stable means you will converge to the origin. That means asymptotically 0. That's the only difference here. Okay, for asymptotically stable, it had to be converged to the equilibrium point. Okay, stable that means it converges to the equilibrium point. It only stay around the equilibrium point. For asymptotically stable, you have to converge to the equilibrium point. Okay.